Hello, everyone. Sorry about that. How is everyone doing? Hello, how's it going? Hey, okay. Is everyone feeling fairly refreshed after the weekend? Well, I guess it's a Tuesday now, so maybe not. Has anyone had any other sessions today or this week? Is anyone's first time? If so, welcome. If not, welcome back. Either way, some type of welcome. Physics for me. Ah, hello, Cricket Crazy. Yes, indeed. We've just done, in fact. Ah, amazing. It's good to see a lot of old faces. Fantastic. No, well, everything's all a bit in the dark at the moment, isn't it? From Friday till today. Oh, damn. Okay. Hello, everyone. I see some people are still kind of filtering in, so we'll give it another minute. Oh, thank you. I'm sure you're a fantastic student too. Hello, my dude. First time here. Oh well, damn, that is some pressure. I'm I'm not sure how I feel about that. We'll see. We'll see how it goes. Hey, well. Okay. No. We're all good. It's all right. I'm backing myself. Don't worry. Okay. Should we do this? I think there's enough of us here. Chauvelin. Okay. Right. Just share my screen with you so you can see what we're doing. So today is a study club on Newton's laws. So it's kind of one of those things that you kind of learn early on, but it's easy to kind of forget some of the subtleties. So sometimes it's a little annoying when you get to a question, they ask something subtle about the laws, and you realize you kind of forgot. So I think this will be quite an interesting one to chat through. So just a quick notice, there'll be a coupon code at the end of the session. So right at the end of the session, I'll give you a little tour of how Snap Revise works, etc. And if you're interested, there is a coupon at the end, so that you can get a cheaper first month with us. So for now, let's smash in with some questions. So we'll just have a little read of this together and have a crack. So in the 17th century, when thinking about forces, Galileo imagined a ball moving in the absence of air resistance on a frictionless track. What a mouthful, as shown in figure 3. So we may have to try and extract some information from this question in a second, because that was quite a mouthful. The slope beyond B was now horizontal. I kind of want to label that on. So from here to here, horizontal. Okay. On the axis below, sketch a speed time. Good. Okay, they've already labeled the axes. That's nice. A speed time graph for the ball from its release at A. Okay, there's A. Until it reaches position X. Okay, here's X. Shown in figure 3. Figure 3. Okay, good. We're looking at the right figure. Indicate on your graph the time when the ball is at B. Okay, so can someone explain to me what's happening here? Can someone explain to me what's going to happen to the speed between B and X, for example? We're drawing a speed against time graph. Actually, one thing, what's the... Nice. What's the... Yeah, what's going to decrease? There's an interesting question. Is the speed going to decrease? I see, yeah. So here we're definitely being asked about speed. So we're just being asked about how fast it's moving. Nice, okay. So first of all, I'm interested in a quick question. What's the gradient of a speed time graph? Speed time graph. Acceleration. Okay, cool. So the way I'm going to approach this is to try and think about what the acceleration is everywhere, and as a result, give the gradient. So between B and X, what's the acceleration? If it's going horizontally, between B and X, what's the acceleration? 0. There's no force on it. The only thing that's speeding this ball up is gravity. It's the fact that it's on a slope and it can be pulled down that it's getting, well, faster and faster because it's being pulled down the slope. After going past B, there's no force that's speeding it up because gravity is just trying to pull it into the ground now. So there's 0 acceleration. So the gradient is 0, or there's a constant velocity. So from X to some time before, it's going to be flat. That's a gradient of 0, 0 acceleration. Or you can see this as, well, it's a constant speed because the speed isn't changing. I have a flat graph. Okay, so we kind of understand the back end of the graph. What is the speed at time equals 0? Maybe we can get another point here. Can anyone find out from the question what the speed at time equals 0 should be? Let's see. Yeah, why 0? Which word in this question is giving us 0? Because it's kind of subtle, I think. Release, good. The ball was released. No one kind of like pushed it. It wasn't thrown. It wasn't already falling and someone started timing it. Somebody released it. Okay, so time equals 0. It was just not moving and then it fell down the slope. So, okay. Now we have to figure out what goes on between this point here and some point here. What do we reckon? I'm going to give you 2 options. Here's option 1. In fact, I'll give you 3 options. Here's option 1. Here's option 2. And here's option 3. What do we reckon? Ah, nice. Good. It kind of looks more natural, doesn't it? Like, even if you don't know the answer, it looks kind of smoother than the other 2. The other 2 kind of had to do something weird and jaggedy at this point here. Okay, so first of all, they kind of asked us to say where B was. And our whole idea was from B onwards, we're flat. So this is like point B. Okay. Now here's the idea. The acceleration is the gradient. So this should be steeper when there's more acceleration. Now, when the ball is higher up, earlier on, there's a stronger force kind of pulling it in the direction of its motion. Compared to here, where most of what gravity is doing is not trying to speed the ball up, it's just kind of pulling it into the ground. So here is where the acceleration is biggest. Here is where gravity is doing the most. Acceleration is gradient. So I think it starts off steep. It starts off with a big acceleration, and then it gets less and less steep. And that looks a lot like option 3. Yeah, so yeah, absolutely right. So if there was air resistance, there'd be a lot of other stuff to think about. It might actually look pretty similar. But yeah, luckily in this question, we won't have to worry about air resistance or frictionless track. Good. Okay. So well done, everyone. Yeah, absolutely. In general physics, there will be all sorts of extra things to worry about here. Okay, good. So I think we have quite a nice, concise answer there. Notice all the time, I think there was a lot of answers at the start which are really natural, which were to imagine some kind of a downwards curve or a decreasing. But we're graphing speed here. And the speed, as the ball goes down the hill, is increasing. But it's increasing at a decreasing rate. Good. Okay, so I think that's a really nice question to kick us off. Let's have a look at a follow-up. 2C. Newton later published his 3 laws of motion. Explain how Newton's first law of motion is illustrated by the motion of the ball between B and X. Okay, so do we have any ideas? So whenever you're given an explain question in terms of a thing, it's very important that you state what that thing is, or at least refer to it. So first of all, the kind of like immediate reaction to this question should be to state Newton's first law. So what does Newton's first law say? An object at rest will stay at rest unless acted on by an external force. Yeah, so here it's interesting, isn't it? We're going to want just the other bit of that law. Yeah, constant speed. Good. So Newton's first law. There's a few ways of phrasing it, but I'll just say this: an object will keep a constant velocity unless acted on by a resultant or net force. So a net non-zero force. Let's just rub that bit out. Okay, so we've stated the law, but we still have to explain why that matters here. So why is this? When the ball is between B and X, is there a resultant force on this ball? Good, absolutely right. There's no resultant force between B and X. So now we've stated the law, we can relate it to our question. There is no resultant force on the ball between B and X. So no change in velocity. Good. Absolutely right. Constant velocity. Yeah, absolutely right. So yeah, I was thinking it'd be nice to point this out actually, because there is still gravity acting on this ball. It's just not in the direction of motion. So there is still like a weight of this ball, gravity pulling it down. But you're absolutely right. It's balanced out. It's balanced out by the reaction force on this thing. Now, when the ball was going down the slope, this wasn't true. When the ball was going down the slope, yeah, there was some kind of a normal reaction force kind of pushing it out like this. the weight was like this and they couldn't completely balance each other out, there was a bit of gravity that pulls it along the slope that had no reaction to it. Yeah, so it's only when the ball was going on the flat bit of the slope that there was no resultant force. We didn't need to mention this. This is just kind of for you guys to understand better what's going on here. Okay, really nice. Well done. So let's have a look at another question. Well done, everyone. During a lesson on, I really like this question. During a lesson on Newton's laws of motion, a student says, we don't really need to bother with Newton's first law because it is included in his second law. State Newton's first two laws. I know you've already got the first law down, so I want you to state the second one. And then explain how Newton's second law includes Newton's first law. Okay, so what does Newton's second law say? Oh, fantastic. This looks great. Really good. Now, when you state a law, I know you would do this in the exam, but just so you know, in the exam, whenever you explain or state something in terms of an equation, it's good to state what the letters stand for. So the examiner knows you know what's going on. So I would say Newton's second law says F equals ma, where F is the resultant force, M is the mass, and A is the acceleration. Good. Okay, if there is no force, there is no acceleration. Good. Yeah, okay. So we want to explain Newton's first law, which says no force implies no change in velocity. So from Newton's second law, I know some of you have said this already, but what does it tell us about the acceleration when F equals 0? When there is no force, well, that means F equals 0. Well, that must mean that ma is equal to 0. Now, assuming the mass is not 0, what does that say about the acceleration? Absolutely right. Good. The acceleration must be 0. And so acceleration equals 0. Now, how does that give me this first law? Well, if there's no acceleration, acceleration is the change in velocity in time. No acceleration means no change in velocity. Good. A equals 0 implies velocity does not change. Yeah, so there's some really nice, some really good answers here. The Newton's second law says when there's no force, there's no acceleration. So when there's no force, the velocity can't change. And that's exactly what Newton's first law said. No force means no change in velocity. Really good stuff. Well done. May lead you to wonder why they're stated as 3 separate laws, which is an interesting question, which we won't go into because it's fraught. You don't agree with Newton's third law? Oh, okay. What's the example? Newton's third law is a little bit of a tricky one. We have some questions on it actually. It doesn't always say quite quite the thing you think it is. It's kind of an odd one. Okay. In fact, the next question is about Newton's third law. So maybe I'll bring this up as a talking point. 1 second. Okay. Good. Okay. So question 3. A steady stream of water strikes a wall horizontally without rebounding. And as a result, it exerts a force on the vertical wall. Yeah, I mean, it's a really hard law to think about, but this is a nice example of it, actually. You may be, well, not quite this one maybe, but we'll come to that. You may be awarded additional marks to those shown in the brackets for quality of written communication. Okay, we won't worry quite so much about this, but with reference to Newton's laws of motion, state and explain why the momentum of the water changes as it strikes the wall. Okay, so it's worth kind of drawing a diagram here. So we've got a wall and we're firing water at it. Say we might imagine with a hose or something. And then it's kind of splashing off or whatever. Cool. Okay. Okay, so with reference to Newton's laws of motion, explain why the momentum of the water is changing as it strikes the wall. Which Newton's laws do you think we're going to refer to here? So, yeah, how do we know that the water, so the water is going to exert a force on the wall, but why does this mean the momentum of the water is going to change? Nice, for every action, there's an equal and opposite reaction. So if the water is exerting a force on the wall, what is the wall doing to the water? Good, okay. When the water strikes the wall, it exerts a force on the wall. As a result, and here's one of these things again when we're doing this sort of question. So the wall gains momentum and the water loses. Haha. Yeah, nice. So why is this? So there's velocity. Good. Yeah, really nice stuff. So there's 2 steps to this question. There's understanding that there will be a force on the water, and there's understanding that as a result of a force on the water, there will be an acceleration on the water. And what does an acceleration do? It changes the velocity. If it changes the velocity, it changes the momentum. So there's a lot of steps to this question. I kind of feel the same, actually. It's good reason to get up. Okay. So let's think about this in steps, because there really is kind of a lot going on in this question. The water stroke, and we want to refer, the question has asked us to refer to these laws of motion. So we absolutely need to mention them in our answer. Exerts a force on the wall. Newton's third law. Then implies there will be an equal opposite force by the wall on the water. As a result, the water is going to decelerate. So Newton's second law notice how I'm making a real effort to refer to these laws. Newton's second law says this force produces an acceleration of the water. Therefore, water changes velocity. So water momentum changes. Since P equals mv. I'll explain this again. Yeah, sure. So we want to explain why the momentum of the water is changing as it strikes the wall. The reason the momentum of the water is changing is because there's a force on it. So we have to explain where this force has come from. So the first thing to say is, as the water strikes the wall exerts a force on the water. That's Newton's third law. Newton's second law says, since there's a force on the water, the velocity of the water is going to change. And since its velocity is going to change, then its momentum will change, because momentum is proportional to velocity. Is that kind of better? It's a confusing law. The more you think about it, the better it becomes. The more examples you try and think of where you think it's probably wrong, because it does just feel wrong all the time, you can always eventually figure out what the equal and opposite force is. There's a couple of very tricky examples. Maybe I'll chuck them at you. No worries. Cool. Okay, so I hope that's a useful answer. It's quite an involved answer, that one. Again, I know I've said it already, but my main point here is kind of how to refer to what they've asked us to talk about in the question. Okay. Now we're asked an additional question. Explain why the water exerts a constant force on the wall. So this 5 marks here is not for this part. This 5 marks is for both answers together. The last question was quite a long one, so this is going to be a very short answer. So explain why the water exerts a constant force on the wall. What do we reckon? So in particular, we already explained that there was a force. So the bit they're asking for us to explain must be the constantness of the force. Why isn't the force changing with time? What do we reckon? Yeah, this is a kind of a funny one. True. So yeah, its mass isn't changing, same speed. Yeah. So this is kind of a weird question. They're looking for us to be very good, very, very lucky at kind of being good at reading the question. So is there a clue in this question that the water isn't changing how? Because put it this way, if I powered up the hose, if I made the hose go faster, for example, and it'd be coming at the wall harder, then maybe it might feel a stronger reaction force from the wall, and then it might have different acceleration and stuff. So there's something in this question that's telling me that the way I hit this water at the wall never changes. Good. So this is a really kind of tricksy question. And it's kind of an annoying one, which is kind of why we got it. Good. So here we were told it was a steady stream. So a steady stream of water, what does this mean? It means a stream that isn't changing in its velocity or its power. Yeah, this is a really tricky thing to spot, I think. So really what they're asking for here is to say, well, the water is flowing at a constant rate towards the wall. Towards wall. Steady means velocity is constant. Good. Okay, water is flowing at a constant rate towards the wall. So force it exerts on wall is constant. So the force it exerts on the wall is constant. This is kind of a silly mess. This is a kind of a silly question in a way. But there you go. Good. Well done, everyone. So let's have a look at another question. Yeah, it's true. The acceleration happening to this water is kind of a constant because it's always going from the same speed to zero in kind of the same time. We don't even need to say this here. We just have to extract this piece of information from the question. Good. Okay, so next question. Figure 2 shows a ball deforming as it contacts the ground, just at the point where it is stationary for an instant and has reached maximum deformation. Okay. Yeah, sure. All good. So there should be some slides as well, but I guess they won't have my answers on them. Cool. Figure 2 shows this ball. Great. Okay. Explain how Newton's third law of motion applies to figure 2. What do we reckon? Equal, so forces at opposite and equal. Force exerted by ball would be equal to the force exerted by the ground. Good. Yeah. And then there's this nice thing to mention. They've been asking about this deformation, so they may well be kind of asking about this. So a ball is deformed as it's hit the ground. So the ball exerts a force on the ground. Why does it exert a force on the ground? Well, it's being pulled into the ground, I guess. Good. Ball exerts a force on the ground, and the ground exerts an equal and opposite force. Good. Explain how Newton's third law. So it's mentioned here. Newton's third law says every force has equal opposite reaction force. So the ground exerts upwards force on ball, causing it to deform. Really nice. Ground exerts a reaction force. Okay. Good. Okay. So we were actually asked here. So here we were asked to explain how Newton's third law of motion applies to the ball. And this is kind of one of those funny questions where you give a kind of a full answer and then you realize the next question wanted some of that answer. And this doesn't matter too much. So the next question says, explain why there is a resultant upwards force on the ball. So here, I mean, we already kind of spoke about Newton's third law and saying there's equal and opposite forces, and we understood enough about the situation already to kind of say what directions things were. So I guess what we really want to do is focus on our answer here and talking about why the resultant force is upwards, for example. So I know you kind of already said this, but how would you try and answer this question? So here, we're not just asking, there's kind of a bit more going on as well, actually. Because we know there's a kind of an upwards and a downwards force on the ball, but there's a resultant upwards force. So altogether, this ball is actually being pushed upwards. So the upwards force is larger than the downwards force here. We want to try and explain this. Good. So usually you would just have like, imagine like a solid ball. Yeah, if you had just like a solid ball on the ground, then you'd be pulling it down with some force. What force is it that's pulling this down? What force is pulling this down? We may as well say this in our answer. What is the downwards force? Gravity, yeah. Or in particular, the weight. Very nice. Okay. Downwards force is the weight. Is weight. Now, what about this upwards force? Nice. Yeah, that's the acceleration due to gravity. Yeah, so I think you're reminding me that if you knew the mass, you could find the weight from gravitation acceleration. Cool. Good. Now, if there's a resultant force upwards, well, what is this upwards force? Have we got a name for it? Yeah, this normal reaction force. Contact force is another word for it, absolutely right, or reaction force, good. So all we need to do here is kind of explain why there's a resultant upwards force. And this is really about being able to understand how to add together vectors. So what we need to tell the examiner is we understand that this is coming from the fact that the normal reaction force is bigger than the weight here. The normal reaction force upwards is larger than the weight. So when the forces are summed, the resultant is upwards. Mm. Mm. Yes. So you would need to kind of say what the forces are. How can there be a resultant force? So this is a really good question. Notice that I haven't talked about Newton's third law here. Is it this downwards force that we're looking at is not that there's two things going on here. Here we're looking at all of the forces on the ball. So it's really good that you're asking this, because this is where the kind of big thing with Newton's law happens. Here we're looking at all of the forces on the ball. Now, this is not something that Newton's third law talks about. Newton's third law says that the force from the ground on the ball is the same as the force the ball exerts on the ground. Now, the force pulling the ball down, let me write this out because this is really important. Force pulling ball down is W. But this is not the force the ball is exerting on the ground. Why? So Newton's third law says whatever the ball exerts on the ground exerts on the ball. Now we're talking about the forces on the ball and just saying, well, the force the ground exerts on the ball is bigger than the force that's pulling the ball down. So it's not just that there's the kind of gravity that's pulling this ball down here, but also the ball has been deformed. So the ball wants to like spring back out. So it's not just being pulled down, but there's like this elastic force in it that's also pushing into the ground. There's kind of two things going on here. Now, they've not asked us to go into the mechanics of this, so we don't have to explain exactly where this extra force is coming from. But just because the force pulling the ball down is W equals mg doesn't mean that the force the ball exerts on the ground is W equals mg. And here, not only does it exert its kind of weight on the ground by sitting there, but it's actually pushing even harder on the ground because it's actually trying to spring upwards. Imagine kind of the difference between standing on the ground. So if I'm stood on the ground, I exert some force on the ground as a result of my weight. If I jump, then I spring my legs down and then I push off the ground to try and come up. And if you imagine there, when you really push off the ground, you're really using your legs to push even harder on the ground than just your normal weight. That's how you spring yourself up. So this is the kind of idea here. Just because I'm being pulled down by this weight G, yeah, it all kind of adds up into one big force. But the point is that if force exerted, good, really good question. So the force exerted by the ball on the ground is more than just its weight. And because there's an equal opposite, now if we want to know about the forces on the ball, there's an equal and opposite force exerted by the ground on the ball. So this force here is a measure of how hard the ball pushes on the ground. This force here is just a measure of how hard the ball is being pulled down. So the resultant force is upwards because this normal reaction is bigger. The normal reaction is bigger because the ball is pushing harder than just its weight down. Yeah, it's really hard. So I'm gonna find, so we're doing okay for time actually. We only have one more question. So let's have one more think on this. So how do I want to say this? Let's imagine a human. I think this is a really nice way of imagining it actually. So I'm going to imagine two situations. One where I'm just stood on the ground. Here, I'm being pulled down by gravity, by a weight, by a force W equals mg. Now, I'm not doing anything special, so I'm getting kind of pulled down this hard, and so this is also how hard I push on the ground. I also push on the ground with just my weight. So I wish I had some more space. So I'm going to draw it here. Okay, I'm going to rub this out so we can say some new stuff. So I'm going to imagine two situations. Sorry about my nose, bad hay fever. Okay. Situation one, situation two. Situation one, pulled down by W equals mg. Sorry. Not only this, but I'm not doing anything else special. So exert that force on the ground. Newton's third law says ground pushes back with same force. With same force. So on the ground, there is a force that I'm exerting on it, which also happens to be W equals mg. And as a result, it exerts an equal and opposite force with same magnitude. So in that situation, they balance. Let's imagine instead that I've compressed my knees and I'm ready to jump. So here I'm like this. I don't know, how do people jump? Like this or something. Now, just as I'm jumping, I'm not just stood on the ground. I'm pushing down on the ground with my legs. I'm really trying to slam into the ground to push myself upwards. So here, sure, I'm being pulled down by gravity by a weight mg. If you look at what's pulling on me as a person. But what I exert on the force is kind of what I exert on the ground is my weight plus whatever I'm doing with my legs, plus kind of leg force, plus the kind of me slamming into the ground with my legs. Now, whatever force I exert on the ground is the force that the ground exerts on me in the opposite direction. So this time, what's exerted up here is, again, kind of my weight plus how hard I'm pushing with my legs. And so here I'm being pulled down. If I look at the forces on me, I'm being pulled down by my weight and being pushed up by something bigger. So that's another explanation of how this elastic ball is working. We may well, I'm not sure what our schedule is. But that's the idea here. So this is really worth kind of thinking about. And I think after this session, kind of let this sit in your head for a bit and go round and round on it. Try and convince yourself it's wrong. Because I think this is one of the hardest things in A-level physics is really trying to understand Newton's third law. So yeah, I hope that's useful. So let's have a go at a last question. The diagram shows, so this is a completely different flavor. The diagram shows 3 passengers sitting on a train that is traveling at high speed in the direction shown. Good, okay. Seatbelts are not used on trains. Misread it. With reference to one of Newton's laws of motion, explain why seat C is the safest seat for a passenger to be sitting on in the event of a rapid deceleration. You may assume that the seats all remain fixed firmly on the floor and do not break. So what do we reckon? Can anyone tell me why you think C is safer? Also, I'm very sorry. I'm just going to blow my nose. I'll be 1 second. Sorry about that. Hay fever is quite something. Person C would just be pushed into their seat. Person A would crash into person B. Nice, yeah. So person A crashing into person B is bad for person A and bad for person B. So I would like to be in person C. Person in CA will be pulled towards the direction of travel. B and C people will be pushed into their seat. So what I love here so far is that everyone understands, everyone has this intuition for who's the best and kind of why. And if you're on the train, it feels like you're kind of being, if you're in C, you're being like pushed into your chair. And if you're A, you're being like launched out of your chair. What's really happening though? Is that really what's happening here? We're being asked to explain this in terms of, yeah, so we're all definitely getting the marks for saying who's got the best thing. But again, it really says with reference to a Newton law of motion. Now, what law? Yeah, I want to think more about this inertia thing. What law are you thinking of when you're thinking of inertia? Law 1. So what does law 1 say in this situation? Yeah, so inertia is a kind of a funny word. Don't worry too much about the word inertia. Just think about this in terms of Newton's first law. At the moment, this person in CA is going to keep on moving in the direction that they're traveling unless a force is exerted on them. So when the train stops, what will the person in A do? What will person A do? When the train stops, the moment it stops, is there any force being exerted on person A? Yeah, it's going to feel like they're flying, but what are they actually doing? Yeah, person A is going to feel like they're flying, but what actually happened? What actually happened is, yeah, they just kept on traveling as they always would. We're traveling at a constant velocity. The train stopped and no force was exerted on person A. So person A just kept on traveling just like normal. But the train itself had stopped. This seat here has stopped and exerted a force on this person here and caused them to stop. They don't keep traveling. So this person feels like they fly out their seat. What they're really doing is Newton's first law. What they're really doing is just not changing their velocity. And that's why they'll keep going as if the train was still moving until they hit person B and have a force exerted on them in the opposite direction. Good. So we need to explain. Good. So it's true that like there's all sorts of other things we can kind of explain here in terms of equal and opposite, in terms of the reason why person B and C stuck is because of the force being exerted on them by the chairs. But the kind of key thing here and what they're really looking for, and I kind of want to stress this, is they don't want anyone to say what's very natural, which is that some kind of a pull happens to person A, that they get flung out of their chair by some force. A would just continue moving as it always should have until it hits B because B has been stopped. Good. But they really want us to understand that no force was exerted on A, causing them to fly out of their chair. They just kept moving as they always would because no force was exerted on them yet. Yeah. So when the train stops, here's B, here's C. I actually probably have to wrap up the session here because we're just running over time. But maybe we can chat about it again in a drop-in. Okay, so this is A, sorry. All I want to mention here is Newton's first law says person A keeps moving because no force is acting on them until they crash into B. but I never said they were flung out of their seat. And that's the important thing here. They just kept moving because no force was exerted. That's kind of what they're looking for here. And so C is the safest. Good, okay. So that brings us to the kind of the end of that bit. Sorry, 1 second. My course is good, okay. So the last thing I want to mention is thanks everyone for that session. You've all been kind of really active, engaged, so it's been fantastic to teach. And this is a really interesting topic to teach. Like I said at the start, it seems simple. It seems so simple, but there's lots of really subtle stuff going on with just those 3 basic laws. So really sit with the stuff that we learned today and try and make sense of it. Exactly right. A has no force exerted on it, so it keeps moving as always. So I'm just going to give everyone a quick walkthrough of Snap Revise now to kind of explain what we try and do for learning on our website. And then I'll give a quick coupon code at the end if anyone wants to kind of see more. We have all sorts of things. We have kind of drop-in and sessions and walkthrough sessions like this, but we also have lots of kind of static online learning and a lot of tools to help you figure out what you need to focus on. So I'll just give you a quick look of that now, because it's pretty cool stuff. So just share my screen. Here we go. So I'm currently in the Snap Revise website. All I had to do here was to sign into the website, make up a mock account. And because I'm signed up, as I am, because I just love doing A-level physics, I have a physics course that I can go to here. In this ultimate course, there's all sorts of cool features. So we can go through year 12, and what do we fancy doing? Let's take a look through. Mechanics and materials. Maybe we can find a good question here. Newton's laws of motion. Let's have a go at that. That seems like a good shout, right? So we get given a quiz, and this is a diagnostic quiz. This isn't just a quiz for us to kind of have a quick look at and check our understanding. It does a lot more. So after doing the quiz, it's going to tell us what to learn and direct us to exactly the bits that we want to be learning. So this is really cool. So let's have a go at a couple of questions. What are Newton's laws used for? Can anyone tell me? Yeah, thanks, Cricket Crazy. Awesome. What do we think the answer is here? So I think the answer here is B. And it is indeed. Okay. So we'll have a look at a couple more, and maybe I'll just guess some and make sure I get them wrong as well. Okay. How much force is exerted by the block on the table? Haha, well, we know this one. Equal and opposite. Good, okay. Let's get some wrong. Be embarrassing. Okay. So at the end, oh, nice, yeah, A and B. Thank you. Good. So at the end of this quiz, we get a kind of diagnostics back. So I'm comfortable with Newton's law and Newton's third law in particular. I got the question on Newton's third law correct, this reaction force one. But from the answers I gave, Snap Revise now understands that I don't understand Newton's third law, first law, Newton's second law, or some things about definition of mass, etc. And this is really useful because Snap Revise has all of these different learning resources available, now they can direct me towards what I should be focusing on. So as soon as I kind of hit start and I say, I want to go, I want to learn now. So I'll just pause this video for a second. Here's where the cool stuff happens. There's all of these different videos that I could look at that would be worthwhile for Newton's laws in general, but it's highlighted in orange the videos that I personally need to look at, the ones that I should spend my time on, the bits that I was confused about. Not only that, but when I go into the video, say I go into this video here, it even tells me which parts of the video I need to take a look at. So in our whole course is split up into segments, and this video here has an introduction to Newton's laws, which I was fine with. Then it talks about Newton's first law, which I was struggling with, which is highlighted in orange. I can click on each section that I need to go through and go through it individually. And I can, for example, choose to skip Newton's third law if I like, because I already smashed this bit in the exam. So this is really useful in the sense of everyone wants to try and optimize their learning. Try and make sure that you spend as much time doing the right stuff as possible, because then you get to spend less time revising as well. You get to learn what you need to learn quicker and hopefully relax a bit more as well. So I know A-levels can be very stressful. So there's an opportunity to comment and reply to various videos underneath as well, which can be useful for kind of understanding your way through any problems that you have with the video. It's also useful for us to see what people are getting and what people are not getting. So this is great. Along with this stuff, there's also exam packs, there's revision guides that you can take a look at, and these are our own self-written things, are all the things that we think are going to be useful for you. So we're really proud of this. We think this is a great service. And I even get a kind of percentage through showing me how far through the course I've got. As you can see, I've already spent some time on this course in my own time, and I'm 21% through. So that's really good for kind of motivation as well. So I'll just give you a quick look at the plans that are available, because there's a few different kind of levels of the things that we do at Snap Revise. So our idea was the following. A tutoring session typically costs, well, can cost around £50 an hour. And this is completely unaffordable for a lot of people. So our idea is to try and take what we believe to be kind of important parts of the tutoring experience and try and spread that cost and make it more affordable. So we have a few different plans. So in our first plan, we have the basic plan. In the basic plan, you have access to all of our resources, all of these static resources. So you can watch our videos and learn from them. You can look at our exam walkthrough videos where we've come up with questions that we think are worth going through and try and lead you through them. So they're not just exam answers, they are a person talking you through the exam question and trying to show you how to extract information properly from an exam question. Because sometimes you know all the stuff, but you've actually got to try and figure out what the examiner wants from you. This can be a bit of a nightmare. We saw a bit of that today. You get access to mini revision guides too. So that's £9 a month, which is certainly very different to £50 an hour. So for £30 a month, still way cheaper than £50 an hour, we include this smart adapting learning quiz stuff. So this is this diagnostic tool that makes it, that we hope will streamline, which we know will streamline your revision and your learning to focus so that you don't end up going through things that you already understand, which is super easy to spend your time doing. We also have some packs of kind of our predicted exam questions, along with some self-marking quizzes. And then there's an ultimate version. So in the ultimate version, we figured how much of the tutoring experience can we try and spread out and make more affordable? So rather than £50 an hour, we said, okay, let's do that for a whole month. And what can we offer for that price? So for £50 for a month, which we're quite proud of what we're able to offer. So we have various kind of additional tutor style sessions, kind of things like we have today, where we have chat windows where you're able to ask questions. We have sessions where we just walk through a particular topic, kind of like we did today. We have ones where we talk about exam questions, a bit more like today. We have ones which are more structured, kind of lessons about a particular topic. So today I did a session on SUVAT and SUVAT equations. And finally, there's drop-in sessions where you can just come to the session. For example, for physics, you can just come to me with some questions. Everyone comes together with questions and we work through them together as a team and try and figure out the answers to your questions. So this is the kind of bit of the tutoring experience that we're trying to offer at a fraction of the usual price, along with this tutor support chat as well. So this is what we have to offer. We're really proud of this because we want as many people to see this as possible, to be able to have a go at using our service as possible. We've got a coupon code for everyone to use. So if I just bring us back, here is the, so here's the upcoming study clubs. You'll be able to see these on our channel as well. We're really enjoying doing these study clubs. So yeah, please come along. The more the merrier. Today was really fun. And finally, here is our code, Newton's Law 10. So thank you so much, everyone, for coming. And I don't know if anyone has any questions. But yeah, thank you so much. Yeah, hope to see some of you there and look forward to seeing as many of you as possible at the next YouTube session. Oh yeah, thank you very much. That was a really enjoyable session. It's really nice when it's really interactive, and if people are confused and asking questions, it means we're learning something. So that was a really good session. Cool. Well, thanks very much everyone for coming and sticking around and listening. Really appreciate it. Okay, great. Well, I think if that's everything, then we'll call that a day there. And I look forward to seeing more of you in the future. Okay, see you around, everyone. Thanks very much. Bye. Yeah, thank you.